So this talk is about a heap dumper for glibc. And why do we need a heap dumper? The main goal for me was to debug anomalous memory usage. That could be memory leaks in the application or unintended allocation behavior where we get heavy fragmentation and the allocator uses memory, an amount of memory that is unexpected by the application developer. But what we also had before was we saw some memory corruption, and we needed to figure out where that was coming from. This particular tool that I have developed doesn't do that, but that could be a future evolution. And what would be really interesting to get type-based memory statistics, but that is kind of difficult to get because you don't have, if you have just malloc and you only have the size and no type information at that point. So the implementation status, what I have today is there's a repository that is linked in the slides. There are basic, main features are there are very basic statistics about arena and heap usage, and you need to have seen Wilco's talk to make sense of most of this, what is going to follow, unfortunately. So each thread has an associated malloc arena, and the association is not one-to-one. One arena can be attached to multiple threads, and the tool is able to show that. We can, for each thread, we can, for each T-cache, we can show where, in which arenas the allocations are placed. We have some concerns that placing allocations into a T-cache that is not corresponding to the arena that the thread uses may have impact on fragmentation. And that is why the tool has some statistics for that. We have size histograms for fast spins, for T-cache, and also if you really want that, for allocations and the unallocated chunks between the allocations. There's no type analysis and no corruption analysis so far. The way this works is we have a fairly broad coverage for glibc versions, only up to 2.41. 2.42 I haven't tested yet, but I suspect that there may be some tweaks needed. What we do is we look at symbols and symbol sizes inside libc SO6, and based on that we make guesses where the critical offsets are. So we don't do any dwarf parsing. That is advantageous because you don't need the full debug info, but we also don't have hard-coded version numbers, so it works across a range of versions, and at certain different versions of our downstream builds that have different feature backports from upstream. So because the symbol sizes and stuff changes, the tool is able to figure out, okay, I'm running on a version that doesn't have T-cache hardening using pointer swiveling, for example. So it still works even if the backports are kind of funky. And the advantage of doing it this way is that once you have a copy of libc SO6, which in our case has a symtab in it, exactly for tools like this, and the coredump, then you're good to go. You don't need the full debug info. You don't need the main program. So that is also kind of interesting for us. We have support for most of our architectures. Porting the tool is quite easy. You just need to describe the register layout in the core file so that the tool can get the thread pointer from the core file. And we need to have knowledge of two relocation types for access to global dynamic data and for computing the thread pointer offset. The tool supports cross-architecture analysis, but it's not cross-environment for now. So it is cross. You can cross across 32-bit versus 64-bit, but not across NDNS. And there's a test suite for it that covers most of the heap parsing. It doesn't work on 32-bit i386 because G-core doesn't write the required thread state into the core file, unlike the kernel. But Andrew Burgess is working on fixing that, and then we have that covered too. I've got some example output here. Yeah, it should be large enough. So it just shows, I think this is for PID1 in it. No, it can't be. It's some other process. I don't remember which. And it shows first some general metadata from the allocator to make sure, okay, we got some useful data out of the whole thing. And then for each arena, basically for each thread, it shows the number of threads that are attached to it. Then, not the number, the IDs of the threads that are attached. Then the IDs of the threads that have T-cache entries from that arena. And then the size of the allocation, the total size of allocated heaps, and the sum of the committed memory in the heaps. And then we have allocation statistics. So that is basically, glibc doesn't have a size class-based allocator. It has flexible allocation sizes. It has to be, and the allocation sizes are always congruent 8 modulo 16, and the minimum application allocation size is 24 bytes. So that's where this starts. And this one shows a pretty good utilization of the heap with 92% allocated. And for the unallocated allocations, we list the fast bin allocations separately from the T-cache allocations. They show up from the lower level allocator perspective, they are allocated, but we present them as unallocated to get the application view. And also we can provide statistics for the gaps as they are encountered, and also the summary statistic that shows that, yeah, in this case, it's a pretty good number. Only less than 5% are wasted in object headers. So that's because the allocations that the application made are fairly large. So for the internals, there's a good overview on this glibc wiki that DJ DeLore created of the internal data structures. And the main thing that enables this approach is that forward heap traversal from lower to addresses to higher addresses is in principle always possible, except when you are in malloc and something is updating the data structures, because we have a chunk header for each allocation, and the chunk header says, okay, this is the size of the following allocation, and you can just skip over it. And fastbin and T-cache are single linked lists and easy to traverse. Fastbin is not unbounded, so in theory the heap dumper can use a lot of memory, but in practice it is a few thousand list entries, even in extreme cases, so that doesn't seem to be a problem so far. And there's a heap traversal implementation that uses basically a lookup table to see what's actually in a fastbin and then treats that as unallocated. Yeah, there's a general theme that the end of the heap is always a bit tricky to discover, so there are some heuristics for that, but I think it's fairly solid and matches what the glibc algorithm actually does. For the secondary arenas, they are split into heaps, and the heaps are linked by a single linked list. And to get to the start of the single linked list, you have to take the top pointer of the arena, mask it to get to the start of the heap, and then there in the start of the heap, there's a pointer to the previous heap and so on and so forth until you get a null pointer, and then you're done with that particular arena. So what we don't have is tracking of mmap-based allocations. So if you do a large allocation and it is not in an arena, then glibc doesn't even track it. So there's no way we can dump information about it. There's some ideas like using heuristics based on the load segments that the coredump contains and try to figure out is this looking like an mmap-based allocation or not. But I think the way forward is to just teach glibc how to track those as well, so that we have better insight into what's going on. And there's a mode in glibc that is currently not implemented. So if there's a break failure and the main arena cannot grow, then glibc can switch to mmap for the main arena as well, and then that needs some special logic, and I haven't really figured out how to implement that yet. What I'd like to export is also a list of allocations. That it would be straightforward to add if you use printf, but you probably want to dump it into SQLite or some of the data analysis framework formats so that it's more digestible. I haven't implemented any consistency checks for bin linking, which uses the metadata in free chunks to verify that there's no heap corruption in the metadata, and that this is consistent with what you get by the heap traversal. This could be quite useful if you want to pinpoint heap corruption. I had an earlier tool that worked like this, but it was for a specific case, and that unfortunately turned out to be not a malloc bug as was initially suspected, but was a kernel bug in the copy on write implementation. So that turned to be a bit of a wild goose chase. Yeah, we also don't have forensic support in the current heap dumper. So if it detects corruption, it has fairly solid corruption checks for what it does. You just can't progress at this point. In theory, you could try to find a free on some free list. You could find a pointer that is at a higher address, and then start from that, scanning from that again, and this way recover from the corruption and not lose everything at higher addresses at this point. But it's not implemented. Okay, that's it. Any questions?
So how do I use this tool? Is it a library?
No. It works on coredumps.
Okay, so it's a coredump. I need a coredump.
Yeah, I mean.
And I run this tool with the coredump, and it extracts the information from the file.
I mean, we can show. So maybe I should do a demo. I didn't prepare this. So I'm just going to dump the memory of the bash process, right? So that is the G-core tool, and I don't have my glasses, so I can't read what I'm typing. So and what was the core file name? Okay, there we go. So it just works on the coredump. And then you have bash is not multi-threaded, so you don't see much there. Okay, any further questions? Any GDB people in the room?
Okay, so but the application finished there, or it's an application that keeps running?
So the G-core tool just writes a coredump for the process without terminating it.
Oh, okay, understood.
And I mean, I could do it like with process attached in some way and do it, or reading procself mem, not procpid mem, and it was just a convenient tool, and we're actually using that to analyze customer support cases.
Mm-hmm.
And then the customer gives us the coredump, and that sort of, or the coredump was there first, and we had to analyze it. So that's the order of events there.
Understood. Thank you.
Is one reason not to build that inside GDB so it can work seamlessly on a core or live process?
So the problem I have with, I can share my slide here, is I've got a bonus slide there that shows some of the problems. So what actually solved the customer case that we looked at here was that we could look at the environment and tell them, okay, you didn't have the glibc tunables activated in that you thought you had activated. But when I use GDB for this, then I need the main program to get the symbol definition for the copy relocated environment variable. And my tool actually reads the relocation data from the coredump for libc-SO6 to see where the dynamic linker has told glibc the environment area is. And then I can use that address to load the actual application view of the environment variable. And the copy in libc-SO6, because of the copy relocation, is 0, because it is the actual pointer is not being written. And not necessarily could have been reallocated if, yeah. And I think this is the missing main program is actually a bit of a problem for coredump analysis in support use cases.
And do you plan to have huge page statistics along with this tool to show which kind of memory is being backed up by huge pages, when either transparent huge pages or direct huge pages are used?
Is this something that is visible in coredumps?
I'm not sure. That's an asking.
Yeah. I don't dump this data today because I think I have logic. I don't know if the huge page support is actually implemented. Good point. Because we generally don't use that. Our distributions use THP in always mode. So we don't use explicit huge pages, so we don't really see that code path. But yeah, there's some code there that knows about the huge page support because it changes the layout of the internal data structures. So I have to compensate for that. Yeah. I don't know if we want to merge this into the glibc tree eventually. For now, it's on the side.
Just a question. So if you do two coredumps, is it difficult enough to actually compare the differences?
The output format is not really amenable to that today. I would have to stop printing the cumulative. I mean, you can see these numbers here at the end, because they can always get a diff if the previous line there was a change somewhere above, and then
they
all
move up and down.
Yeah, okay. But I could add this as I mean, you just dump fewer information and then you can start diffing it. Yeah. Okay. And these output files are not that large, even for very huge processes.
Thank you.
Okay. Anything? Yeah. Anything else? Okay, then. Thank you.